Hey students, this is it, the last of the new material for this quarter. So all that's left now is to take the final and go on a Christmas vacation. So let's get to it. We studied differential equations last time and we talked about separable differential equations. Now differential equations, they're used to model a lot of physical phenomena. So DEs, differential equations, are used. I mean, the whole point of them, or at least one of the main points of them, is that they actually model physical situations. So differential equations are used to model physical phenomena. Now, the one that we want to consider, so we consider the following. So the differential equation that we're going to look at today looks like this: dy dt equals k times y. Now, I chose t because we often are going to think of the variable for our function as time. Not always, but most of the time, or often. Now, what is this saying? Well, it's saying, on the left-hand side, the rate of change of our function y, so the change in y, let's see, it's a constant multiple of y. So the change in y is proportional to y. In fact, let's write that down. Change in y is proportional to y. So this differential equation has a name. So this differential equation is called either the natural growth or decay. So the law of natural growth / decay. So it models growth in the case that k is a positive number. It measures decay, things shrinking, in the case that k is a negative number, right? When k is positive, what we have is a positive derivative, and when k is negative, we have a negative derivative. So, so here is growth when k is greater than 0, and it is decay for k less than 0. So now if you notice, so this differential equation is a separable differential equation. So we can separate it. So let's get an actual solution. And in fact, last time we did go through the process of finding a solution. I just want to do this one more time. So we'll see how this comes about. So if we separate the variables, what we get is a dy over y equals k times dt. Right, now we can take the antiderivative of both sides, and what we'll get is natural log absolute value of y is equal to k times t plus some constant. Let's call that constant d. And then if we exponentiate both sides, what we get is absolute value of y is equal to e to the kt plus d. Using a rule of exponents, we can write this as e to the kt times e to the d. And then what we do is we notice that e to the d is a constant. And so we can write this as, well, let me do one more step here. So let me write this now as y equals e, whoops. What I want to do is get rid of the absolute value. And so if I do that, what we get is y equals plus or minus e to the d times e to the kt. Now notice e to the d is positive, right? And the exponential function always gives us a positive output. And so what we have now is plus or minus e to the d. What that gives us is all possible constants except 0. And so I can rewrite this constant right here as c times e to the kt, where c is any non-zero constant. Now, one thing you might want to know is, well, what exactly is C? Who is this C? So notice this, if we plug 0 in for t, what we get is y of 0 equals c times e to the 0, which is equal to c. So that tells us that c is equal to y of 0, which is the sort of the output at time 0. And so a way to write this equation, y of t, or the solution to the equation, y, the name of our function is y, so y of t is equal to y of 0 e to the kt. And this captures then all possible solutions to the equation. Okay, now what we want to do is we want to study how this can actually be used in physical situations, in real world situations. So the first of the applications, population growth. So it's reasonable to assume if you've got some population, it could be humans, it could be some collection of animals, could be bacteria, whatever, it's natural to assume that the population grows in proportion to the population. Right? The change in population is proportionate to the population, which means if you only have a few people, then the population by reproduction is only going to expand slowly. If you have a whole bunch of people and all of them are reproducing, that population will grow much faster. So the change in the population is proportional to the actual population, right? So let's say it like this: it is reasonable to assume that population, or I should say change in population, so change in population, and let's call that population capital P, is proportional to P. And so the way you would write that then in terms of differential equations, dp dt is equal to some constant multiple of p. Right? So let's say that the population is human beings, or let's say in the country, in the United States. Right? So if we had a million, forget United States, let's say we have 1 million people, then the change is going to be the change in the population is going to be some multiple of that population. And so if this population has 10 million people, right, then the change is going to be much, much faster than, or the actual growth in the population will be much greater than if there's only 1 million people. So let's just try an example now. At 1 p.m., a culture of bacteria has 1,000 cells. At 2 p.m., so 1 hour later, the culture has 6,000 cells. So assuming that the growth is proportional to population, meaning that this differential equation models the behavior of the bacteria, what we want to do is let's find the population at 6 p.m. So find the population at 6 p.m. Okay, so if we assume that this differential equation models the behavior, then what that means, right, is that we can use that solution right there. So what we have is that P of t is equal to P of 0, our initial population, times e to the kt. Now our first job is to figure out what the k is corresponding to this population. And we have this extra piece of information right here. We know that at 2 p.m., 1 hour later, right, we've got 6,000. So what that means is that 6,000, which is P of 1 hour later, think of this as time 0, 1 p.m., and so at 2 p.m. that's time 1, P of 1, and we know that that is going to be 1,000 times e to the k times 1. So now I need to figure out what k is. So k, if I solve, well, e to the k is equal to 6, which means that k equals natural log of 6, and that's about, what is that? That's about 1.8. So what we have is we have an equation that models the growth of this particular colony of bacteria, and it goes like this. At any time, the population at time t is going to be 1,000, that's the initial population, times e to the 1.8 t. All right, now what we want to do is, once we've got our k, we can answer questions about this now. So find the population at 6 p.m. Well, 6 p.m. is 5 hours later, so what we want is P of 5. P of 5 is 1,000, e to the 1.8 times 5, and I work this out, it comes out to be, so it's about 8,103,084. So, we started off with 1,000 cells. 5 hours later, we're up to 8 million some cells. Okay, so there's one place that our differential equation models the physical behavior. Another one is half-life. So that's the one we'll talk about next, is half-life. So the decay of radioactive substances is proportional to the amount, the remaining amount. So proportional to the remaining amount. So what you have, if you have some radioactive substance, let's say like uranium, if you have a certain amount, it's continuously decaying, and the rate of decay is proportional to the amount that you have at any given time. So decay, the way we measure this, so decay is measured in half-life. Right, so this gives us a sense of how quickly or slowly it decays. So the half-life of a substance is the time required for a given amount to be reduced by half. So let's say that you've got 1 kilogram of a given radioactive substance, right? After a certain amount of time, there's exactly half of it left. The amount of time, the length of time that it takes to go from that kilogram to half a kilogram, that's called the half-life. So let's try an example. And by the way, so we said that it's proportional to the remaining amount, meaning that our differential equation is operative in this situation also. So our example here, the half-life of plutonium 241 is 14.4 years. Now what we're going to do is we're going to start with 100 grams. So if we start with 100 grams, and there's going to be a part A and a part B here. So part A, how much is left after 3 years? And part B, how long will it take to be reduced to 2 grams? Oh wait, did I say 2? I wrote 2, but I think I meant 20 years. Yeah, I wrote 2 on my notes, but I really meant 20. My solution has 20. So let's change that. How long? Oh, good, I didn't write it down. How long will it take to reduce to 20 grams? Okay, so first thing we need to do is find K. So before we start A or B, we need to find K. So what we know is that the amount, let's say amount at time t, is equal to the amount at time 0. We're starting with 100 grams. And then we have e to the kt. We need to figure out who this K is. And it tells us the half-life is a certain number of years, 14.4 years. So if we started off with 100, after 14.4 years, we'll have 50 grams. So what we get then is 0.5 equals E, oops, sorry, right here, instead of T, I need to have a 14.4. Divide both sides by 100, we get 0.5 equals E to the K times 14.4. Take the natural log and solve, and what you'll find is that K, let's see, K is going to be natural log of 0.5 divided by 14.4, and that comes out to be negative 0.048. Negative 0.048. So now the equation, or the formula, the function that determines the amount at any given time t, we have A of t equals 100 e to the minus 0.048 t. Okay, now we can answer our questions. So how much is left after 3 years? Well, we just need to know then what A of 3 is. And that's 100 e to the minus 0.048 times 3. If you stick this in your calculator and crank it out, what we get is 86.6 grams. And then for part B, how long will it take to reduce to 20 grams? So now we would have 20 equals 100 e to the negative 0.048 t. And our job now is to find t. How long does it take to have an amount of 20? And if you solve in this case, t comes out to be 33.5 years. So 33 and a half years later, right, we're down to 20 grams if you start with a chunk of 100 grams. Another application, right, and this is the last of the examples. There are many applications to this natural growth rate equation, or the law of natural growth and decay. And so let's do one more, and this one's called Newton's, well, let's go like this, so Newton's law of cooling. And the way it goes is the rate of cooling of an object is proportional to the difference between the temperature of the object and its surroundings. So we can write that as a differential equation like this. The change in temperature, that's the rate of cooling, is proportional, so that's a constant multiple of the temperature, or the difference in the temperature of the object and its surroundings. So T sub S, let me say who that is. So where T sub S is the surrounding temperature. So here's the idea. If you take something out of the refrigerator and it's at a given temperature, and you set it in at room temperature, versus put it in the oven, right? At room temperature, it's going to cool at a certain rate. If you put it in the oven, I said just cool, didn't I? It's going to heat up at a certain rate. If you put it in the oven, it's going to heat up at an even faster rate because the oven is warmer. So let's try an example now. So a glass is filled with water. That is 44 degrees Fahrenheit. Room temperature is 75 degrees Fahrenheit. Actually, the room temperature right now, I'm in slow on Labor Day. Today is, September 8th, I guess. It's a heat wave right now. Well, today I think in slow it was about 102, right? Yesterday I think it made it to 120, so it's definitely not 75 right now. In my office it feels like 90, 95 probably. But I want to get this lecture over with before classes start, so I'm here to get it done. Okay, after 1 hour, the water is at 62 degrees Fahrenheit. So part A, what is the water temperature 2 hours later? And part B, how long will it take for the water to be at 73 degrees? So how long will it take to get to 73 degrees? Now notice, this is slightly different, right? I mean, this is not exactly the same as the original equation we wrote down because now we have a T minus T sub S. So what I'm going to do is I'm just going to use the information we have here, go back to this differential equation and just go through the solution rather than writing down a general formula for the solution. Right, it's easy enough to solve. So let's see what we have. The change in temperature is proportional to the temperature, or the difference in the temperature and the surrounding temperature. In this case, we have 75, so it's going to be T minus 75. And let's just separate the variables and solve. So what we have is dt over T minus 75 equals K dt, which means natural log, absolute value, T minus 75 is equal to KT plus some constant. Then you get, so we've seen this before, T minus 75 equals, it'll be CE to the KT. And let's see how I want to write this. Oh, right. Now, notice that the temperature here is always going to be less than or equal to 75, so this is negative right here. So what we'll have is, when we get rid of the absolute value, T minus 75 equals negative CE to the KT. And so in final form, well, not quite final form, but what we have is T is equal to 75 minus CE to the KT. So there's two things I need to find. I need to find C and K before I can answer any of these questions. So the first thing, right when we take it out, or right when we pour the glass, what do? We started off with 44. So we know that 44 is equal to our initial temperature, and that's equal to 75 minus C. So that tells us that C is equal to 31. So now we know that T of T is 75 minus 31 E to the KT. Okay, now I need to find K. And I need to use this next piece of information right here, the 62. So after 1 hour, the temperature is at 62. So we have 62 equals T of 1, which equals 75 minus 31 e to the k. And so now if you solve for k, so what is it going to be? 31 e to the k is equal to 75 minus that is 13. So e to the k is equal to 13 over 31, which means k is natural log of 13 over 31, which is about, where'd it go? Negative 0.87. So the equation that tells us, or sorry, the formula that tells us the temperature at time t is going to be 75 minus 31 e to the negative 0.87 t. Okay, so now we want to know what's the water temperature 2 hours later. So part A, we're just looking for t of 2. So that'll be 75 minus 31 e to the minus 0.87 times 2. And if you work this out, it comes out to be about 70 degrees. Part B, now we want to know how long does it take to get to 73. So we say 73 equals 75 minus 31 e to the minus 0.87 t. Solve this equation for t. That tells us how long it takes. And it's, if you crank it out, it comes out to be, so do the solution here, t approximately equal to 3.1 hours. Okay, that's it. So you made it through calculus. Congratulations. Well, Calc 2. So I will see you. We'll do a review session next, and we will then have the final. Just the finals on the Monday of, I believe the final is Monday of finals week. So I want to say that's November 30th. But remember, I'm talking on, this is September 8th. And so it's a few months of the future from when I'm actually recording this video. Okay, so, well, congratulations.